We saw that insertion sort had an efficiency of order n squared. Well, what other kinds of efficiencies are there? Well, here's a table that shows some of the common ones and some of the names that we use to describe that level of efficiency. They're ordered from fastest or most efficient to least efficient. And there are more than what's shown here, but this is a good sampling of the common ones. So for example, if you have an algorithm that's order 1, we call that a constant time algorithm. And what that means is no matter how large your input is, it always takes the same amount of time in order to do that algorithm. So for example, to find the first element in an array, that's always going to take the same amount of time regardless of how big your array is. Order log n is called logarithmic time. That means that as the size of your input grows, the amount of time that it takes to do your algorithm grows as well, but it's growing slower than the size of your input. That's good. Order n means that your algorithm is linear. Linear means that if your input size doubles, then the amount of time it takes to do something doubles. This is what you would hope all of your algorithms would be like. But in fact, it's not really true. Some of the algorithms that we're most interested in grow their time, the amount of time it takes to complete them grows faster than your input, which is an unfortunate side effect, but just one of the things that makes computer science challenging. After order n, you might get order n log n. That's called log linear. So some input grows. As your input gets larger, the time it takes isn't quite double, isn't quite twice as big, but it's larger than the time it takes. It's larger than your input. Order n squared is what we saw selection sort is. That's called quadratic. Order n cubed is called cubic time. You might have order 2 to the n, very bad. That's called exponential. And then you might have order n factorial, which is an extremely bad outcome because it means that your time it takes to do an algorithm is growing very, very fast compared to your input. Move right. A second algorithm that's like selection sort, but it's almost like you flip it around, is called insertion sort. And in insertion sort, you also have this idea of cutting down this tail in order to make your problem smaller and smaller. But instead of looking through the tail for the smallest element, you assume that everything in the head of your array is sorted. And you pull the first thing off the tail and you put it where it belongs in the head. And so in this example, what we do is we start with an array that has 11, 9, 16, 5, and 7. And we assume that 11 is in the right spot, but 9, 16, 5, and 7 aren't. So we take out the next element, 9, and we put it wherever it belongs in the sorted section. So in this case, it belongs before the 11, so we put the 9 before the 11. Then our tail has gotten smaller, and we pull out the 16, and we say, well, where does the 16 go between the 9 and the 11? It goes at the end. So we put it there, and we shrink our array. We shrink our tail by 1. Now we pull out the 5, and we say, oh, where does this go? Oh, it has to go at the beginning, and we bump everything down to the left. Finally, we have one element that we haven't picked out yet, the 7, and we say, where does it belong? It belongs between the 5 and the 9. So we drop it in between the 5 and the 9. Although that's sort of funny because our slide is wrong there. Oh well, our slide is wrong. It should go between the 5 and the 9. So what is this like? Move right. This is like the algorithm that you use when you're sorting cards. For example, you pick up a deck of cards, and what most people do is they take one card and they put it on the left where it belongs. And they take another one and put it where it belongs, and another one. So in that way, you kind of end up naturally doing an insertion sort when you are sorting a deck of cards. Insertion sort, even though you do it a different way, ends up having the same efficiency as selection sort. It's also order n squared. Let's take a look at the code for that and see if we can figure out why.